No one expected a single fossil to shake the foundations of human evolution, but that's exactly what happened in 1972. In the harsh, sun-bleached lands around Lake Turkana, once called Lake Rudolph, researchers uncovered a skull that didn't fit into any familiar category. It wasn't quite Australopithecus, but it didn't match the early Homo fossils either. It felt like a species caught in the middle of an evolutionary gamble, combining traits that shouldn't coexist in one creature. But before we jump back in, drop a comment letting us know what time you're tuning in and where you're watching from. We love seeing how far our episodes are reaching, and don't forget to hit that subscribe button. It really helps us keep bringing exciting topics here on the Primal Roots channel. Back then, the story of our origins sounded simple. More tools, slightly bigger brains, lighter faces, and a smoother path toward becoming human. Scientists loved narrating that progression, as if evolution moved step by step, upgrading one version before releasing the next. But the Earth rarely follows neat scripts. The skull labeled KNMER 1470 forced everyone to rethink the beginning of the Homo lineage. The fossil revealed a broad face with strong cheekbones, a surprisingly roomy brain case, and a jaw built for heavy work. It looked advanced in some ways and surprisingly primitive in others, as if nature had mixed elements from different species into one experiment. That fossil would eventually be named Homo Rudolfensis, a species that still fuels debate and confusion more than 5 decades later. To understand where it came from, you have to imagine the East African landscape as it existed nearly 2 million years ago. Today, the Turkana Basin is dry, hot, and unforgiving. But in that distant past, it was a patchwork of wetlands, open grasslands, scattered forests, and winding rivers. Herds of ancient mammals roamed the plains. Giant predators patrolled the shadows, and various human relatives, each with different diets, bodies, and behaviors, lived side by side in a tightly packed evolutionary neighborhood. Homo Rudolfensis wasn't the only human around. Homo habilis moved through the same terrain, shaping simple stone tools that opened new possibilities for survival. Paranthropus boisei, with jaws built like biological machinery, crushed plants so tough that modern humans wouldn't even try to chew them. And remnants of late Australopith still clung to life, climbing trees when needed, but walking upright with surprising confidence. Instead of a single clean evolutionary line, the region looked like a tangled bush full of competing branches, some rising, some fading, others splitting off into dead ends we're only now discovering. That's why the 1470 skull caused a stir. Its mix of traits didn't align with habilis, yet it clearly didn't belong to Paranthropus. The brain, somewhere between 630 and 750 cubic centimeters, was too large for an Australopith. But the wide face and strong dental structure pointed in another direction entirely. It felt like evidence of an alternative path inside the Homo family, one that thrived for a time and then vanished without leaving obvious descendants. Scientists began asking harder questions. Was the rise of Homo a single event, or did it split into multiple lineages almost immediately? Could different groups have experimented with bigger brains at the same time? Was intelligence evolving in parallel rather than in sequence? Those questions turned Homo Rudolfensis into a mystery that refuses to settle. Some experts argue that it's just a larger, more robust version of Homo habilis. Others are convinced the differences are too large to ignore, and that Rudolfensis was its own species, shaped by a unique blend of diet, climate, and environmental pressures. Back then, East Africa was anything but stable. Shifts in rainfall, sudden climate swings, and dramatic changes in vegetation reshaped the landscape again and again. Any species that hoped to survive had to be flexible, either by specializing to extremes or by adapting quickly to whatever the environment demanded. Rudolfensis seems to have followed the second path. Its anatomy suggests a creature capable of eating tough plants when necessary, but not restricted to them. A generalist in a world of specialists. That versatility might have been its greatest advantage, and also the trait that makes it so hard to classify today. Even now, every new fossil from Turkana has the potential to rewrite the story. Rudolfensis remains in the uneasy space between what we know and what we guess. It represents a period in which human evolution was messy, experimental, and full of branching possibilities, many of which vanished long before Homo sapiens appeared. And that's why its discovery matters. It shifted the focus away from the idea of a straight evolutionary ladder and toward a more complex, branching, unpredictable reality. A reality in which multiple versions of early humans tested different solutions to the same challenges. In the next chapter, we dive deeper into this competitive world, where Rudolfensis lived side by side with habilis, paranthropus, predators, and a constantly changing environment that shaped every species trying to survive its brutality. The world that shaped Homo Rudolfensis was far from stable. Between 2.4 and 1.8 million years ago, East Africa stood at the center of one of the most dramatic ecological transformations on the planet. Lake shores expanded and shrank with sudden violence. Forests appeared and vanished within a handful of generations, and the vast open plains shifted from life-rich green to desolate dust without warning. Nothing remained constant except change itself. In this unpredictable environment, several human species lived side by side, each trying to solve the same challenges in its own way. Their coexistence created one of the most complex evolutionary arenas ever documented. The Turkana Basin, stretching across modern-day Kenya and Ethiopia, was the heart of this ancient puzzle. Today, the region looks dry and unforgiving, but layers of sediment reveal a different past. It was once a patchwork of wetland corridors, seasonally flooded grasslands and forest belts clinging to volcanic ridges. Animal tracks from antelopes, early elephants, ancient bovids, and large carnivores show that these landscapes supported dense populations of wildlife. Fossil pollen trapped in sediments reveals waves of woodland expansion followed by abrupt collapses, a rhythm driven by climate cycles tied to Earth's orbit. These fluctuations created ecosystems that shifted faster than species could fully adapt, forcing constant experimentation. Homo Rudolfensis emerged in the middle of this instability. Its traits hint at a species designed for versatility rather than specialization. The wide face, broad palate, and large molars show the ability to crush tough vegetation. Yet its relatively expanded brain suggests a shift toward flexible behavior, allowing it to respond to scarcity in ways that purely specialized species could not. In that sense, Rudolfensis stands at a crossroads, an organism still anchored in the robust, chewing anatomy of earlier hominins, but already moving toward the cognitive strategies that would later define the Homo lineage. This crossroads becomes clearer when considering the other hominins sharing the same space. Homo habilis, often viewed as one of the earliest tool users, occupied overlapping territories. Its skull was smaller and its face more delicate, suggesting diets that relied more heavily on softer foods or on food preparation techniques using stones. Teeth wear patterns indicate an increased dependence on cut meat and processed plants, implying a lifestyle shaped more by behavior than by brute anatomy. In contrast, Paranthropus boisei lived as an extreme specialist. With massive jaws, thick enamel, and chewing muscles anchored to a skull built for force, it thrived on fibrous plants, tough stems, and abrasive roots. Its anatomy was so specialized that it earned the nickname Nutcracker Man. Despite what these differences imply, these species did not occupy separate worlds. They foraged along the same lake shores, moved along the same migration routes, and drank from the same shrinking water sources during droughts. Their footprints sometimes appear preserved in the same layers of sediment, offering a silent record of how close they lived to one another. The boundaries between their territories were not fixed lines, but fluid zones shaped by rainfall, shifting herds, and the unpredictable pulse of the lake. In an environment like that, coexistence demanded constant negotiation. Climate-driven shifts played a major role in these interactions. When the region entered a wetter cycle, forests expanded and food became plentiful, allowing multiple species to thrive side by side with minimal competition. But during dry periods, waterholes shrank into isolated refugees. Vegetation thinned, forcing hominins and animals alike to converge around the few places where survival was still possible. These compression events intensified competition, raising the stakes for any species unable to diversify its diet or migrate long distances. For Homo rudolfensis, dietary flexibility was a crucial buffer. Microscopic scratches preserved on teeth suggest a varied menu: tubers, hard seeds, soft fruits when available, and possibly meat or marrow scavenged from carcasses left by big predators. This mix implies that its survival strategy was not tied to a single resource. A generalist lifestyle offered resilience, but it also placed the species in direct contact with other omnivorous hominins, including habilis. Both likely scavenged the same carcasses, competed over the same workable stone, and followed the same animal migrations. The overlap created constant evolutionary pressure. Predators further complicated this world. The landscape was home to saber-toothed cats, early hyenas with bone-crushing jaws, crocodiles large enough to drag hominins into the water, and raptors capable of seizing smaller animals. These predators shaped the daily rhythm of early humans, dictating when and where they moved. Fossil sites show clear signs of predator-scavenger interactions: bones with tooth marks from carnivores followed by cut marks from stone tools, and sometimes the reverse sequence. These patterns suggest a dynamic in which hominins moved quickly to exploit what predators left behind, but also risked becoming prey themselves. This constant tension may explain why early Homo species appeared to refine cooperative behavior earlier than expected. Groups that coordinated movement, maintained vigilance in open spaces, and protected vulnerable young had a distinct advantage. Cooperative foraging, even in its simplest form, increased access to food and reduced risk. Although there is no direct evidence of verbal language, changes in brain organization hint at growing reliance on gestures, vocal signals, and shared awareness. These abilities would have strengthened group cohesion in a world where survival depended on anticipating danger. The geological forces shaping the region contributed to the complexity of this evolutionary stage. The East African Rift, still active today, created a landscape full of volcanic flows, shifting river courses and rapidly accumulating sediments. This geological activity preserved fossils in exceptional detail, but it also meant the environment underwent sudden transformations. Volcanic eruptions deposited ash layers that altered soil chemistry. Earthquakes shifted drainage channels overnight, redirecting water supplies. Hominins living in this setting had to respond quickly to disruptions, sometimes relocating entire groups to follow newly formed river paths or areas with fresh vegetation. Under these conditions, Homo rudolfensis occupied a unique position between adaptability and vulnerability. It was versatile enough to exploit a variety of food sources, but lacked the extreme specialization of Paranthropus, which allowed that species to endure certain environmental stressors. At the same time, Rudolfensis lacked the more advanced mobility and body proportions that would later give Homo erectus a decisive advantage. If mobility was limited, the species may have struggled to track migrating herds or escape deteriorating habitats during extended droughts. Competition with Homo habilis added another layer of pressure. With its greater reliance on tool-based strategies, habilis could transform raw materials into resources inaccessible to species relying strictly on anatomy. Simple stone flakes allowed habilis to cut into carcasses quickly, access marrow-rich bones, or slice roots with greater efficiency. If Rudolfensis did not participate as actively in tool-making, it would have been at a disadvantage in resource competition, especially during dry periods when every calorie counted. Even slight differences in food acquisition efficiency could shape long-term evolutionary outcomes. Yet the evidence indicates that Rudolfensis was not a passive participant in this environment. Its larger brain volume implies a species capable of flexible responses and problem-solving. Even without direct associations between tools and its fossils, it is unreasonable to assume that Rudolfensis ignored the technological innovations surrounding it. Observational learning, imitation, and opportunistic use of tools may have been part of its behavioral repertoire. The challenge is simply that the archaeological record does not preserve the full complexity of hominin behavior, especially for species that did not leave repetitive, structured tool sites. Social organization likely played a central role in how Rudolfensis navigated this mosaic of rivals and challenges. Larger brains correlate with prolonged childhoods, which in turn require greater cooperation within groups. A species with a slower developmental pace must protect and invest in its young to ensure survival. Such care would reinforce social bonds and accelerate the transmission of knowledge across generations. These dynamics become even more significant when predators are abundant and when neighboring hominin species occupy the same foraging territory. In that context, group structure becomes not just a social trait, but a survival necessity. Beyond survival, the daily movement patterns of Rudolfensis shaped its place within the ecosystem. Lakeshore regions provided access to vegetation and animal tracks, but they were also some of the most heavily trafficked areas by predators. Forest patches offered shelter but were fragmented by seasonal changes. Open savannas provided visibility, yet exposed hominins to extreme heat and ambush risks. Navigating these environments required strategic decision-making, choosing when to remain hidden, when to approach water sources, and when to follow migrating herds. Footprint evidence from related species reveals winding paths rather than straight routes, suggesting that ancient humans constantly adjusted their movements to balance safety and opportunity. Interactions between species extended beyond competition. For some resources, indirect cooperation may have occurred. When Paranthropus stripped vegetation that Rudolfensis could not digest, the disturbance could reveal edible shoots or roots accessible to more generalist feeders. When predators hunted large herbivores, their leftovers became valuable sources of nutrients for any hominin brave enough to approach. The ecological web tied these species together, even when their goals diverged. As the climate cycles intensified toward the later part of the species' existence, a new competitor began to emerge: Homo erectus. Taller, longer-legged, and built for endurance, erectus represented a shift toward high-efficiency mobility. This species could travel long distances across open landscapes, following herds and exploiting widely distributed resources that stationary or moderately mobile species could not. Their arrival marked a turning point, as erectus occupied ecological space that Rudolfensis once used. Even without aggressive interactions, greater range and stamina allowed erectus to outcompete slower or less versatile species over time. In this dynamic setting, the fate of Homo rudolfensis was likely sealed by cumulative pressures: shifts in vegetation patterns, increasing aridity, competition with habilis and erectus, and the rise of more sophisticated tool users gradually shrank its ecological niche. Yet its presence during a crucial evolutionary window reveals that the emergence of the Homo lineage was not a linear path, but a branching network of experiments. Each species tested different strategies, and only some succeeded in the long run. Understanding Rudolfensis in this context highlights the diversity and unpredictability of human evolution. Its world was crowded with rivals, predators, and environmental hazards, forcing constant adaptation. It lived at a time when multiple human forms coexisted, each navigating a landscape that reshaped itself with relentless speed. In that sense, its story is not just about one species, but about the larger process: the evolutionary competition, cooperation, and ecological pressures that shaped the first chapters of humanity. In the next chapter, the anatomy of Homo rudolfensis takes center stage. The structure of its skull, jaws, brain case, and facial morphology reveals the deeper mechanics of how it lived, what it ate, and how it functioned within its unpredictable world. These anatomical clues, pieced together from fragmentary fossils, illuminate the hidden tensions between robust chewing forces and expanding cognition that defined this enigmatic species. The fossil record of Homo rudolfensis is incomplete, yet every fragment that does exist reveals a body shaped by the tension between old evolutionary patterns and emerging innovations. Its anatomy stands at a crossroads between the robust physicality inherited from earlier hominins and the cognitive expansion characteristic of the genus Homo. In this transitional form, clues appear that illuminate a species adapted to unpredictability, shaped by shifting climates and the presence of multiple rival lineages, occupying the same landscapes. The morphology of Rudolfensis is a testimony to a world in motion, one where survival depended on balancing physical endurance, dietary flexibility, and the earliest sparks of enhanced cognition. The most striking element of this species is the skull known as KNMER 1470. When researchers first reconstructed it, they were confronted with an unexpected combination of traits that resisted simple classification. The face is unusually broad for a member of Homo, wider than that of Homo habilis, and even approaching the dimensions of some robust australopiths. This breadth reflects strong zygomatic arches, bony structures that anchor the masseter muscles, which are essential for powerful chewing. These arches flare outward, forming a large midfacial platform capable of distributing heavy chewing forces across the skull. The implications are clear. This species regularly processed foods that required extended grinding or crushing, such as fibrous stems, tough underground tubers, and seeds with particularly resistant shells. Yet this same face is paired with a brain case significantly larger than one would expect for a hominin with such robust chewing adaptations. Estimates place its cranial capacity between 630 and 750 cubic centimeters, considerably larger than most australopiths and overlapping with the upper range of Homo habilis. This expanded endocranial volume suggests more than simple anatomical variance. It marks the growth of neural regions associated with spatial awareness, problem-solving, motor coordination, and environmental adaptability. The juxtaposition of a robust chewing apparatus with an enlarged brain challenges traditional assumptions that facial reduction and brain expansion must evolve together. In Rudolfensis, these trends operated on separate evolutionary schedules, shaped by selective pressures that pushed anatomy in multiple directions at once. The frontal bone, the region above the eyes, offers additional insights. Though sloped compared to modern humans, it is less retreating than in earlier hominins, hinting at the gradual reorganization of frontal lobes. These changes would have supported improved planning, attention, and social responsiveness. Slight expansion in the temporal region indicates increased capacity for processing auditory and visual information, essential for coordinating actions within groups and navigating complex environments filled with predators. These signals point toward a species beginning to integrate higher-order behavior into its survival strategies, even while still relying heavily on physical adaptations inherited from older lineages. The orbits of Rudolfensis, the cavities housing the eyes, are forward-facing and relatively large. This configuration enhances binocular vision, improving depth perception and precision hand-eye coordination. Such traits imply that the species was adept at identifying edible plants, selecting appropriate stones, interpreting subtle movements in the grass that signaled predators, and navigating environments that alternated between dense vegetation and expansive open plains. Although the archaeological record has not yet confirmed systematic tool use, nothing in the anatomy suggests limitations that would prevent Rudolfensis from manipulating objects with deliberate intent. The maxilla and mandible reinforce the portrait of a species capable of enduring varied nutritional landscapes. The palate is broad and deep, leaving room for large molars arranged to optimize grinding efficiency. The thick enamel and expanded occlusal surfaces of these teeth indicate repeated stress from chewing abrasive materials. Microwear analysis reveals patterns consistent with mixed feeding strategies: hard seeds during dry seasons, softer fruits in wetter cycles, and underground storage organs when surface vegetation declined. This versatility matches the unstable climate of the Turkana Basin, where dietary rigidity could become a fatal disadvantage. Instead of evolving extreme specialization like Paranthropus, Rudolfensis took a middle path, relying on both anatomical robustness and environmental flexibility. While cranial remains form the core of its fossil identity, what little is known about the postcranial anatomy provides additional context. Although no complete skeleton exists, comparisons with closely related species offer plausible reconstructions. The limbs were likely proportioned similarly to Homo habilis, with legs capable of efficient bipedal locomotion, but not yet optimized for the endurance-running characteristic of Homo erectus. Shoulders and arms maintained some primitive features, possibly retaining climbing abilities inherited from Australopith ancestors, even if climbing played a secondary role in daily life. This blend of functional traits suggests a species able to exploit diverse terrain, moving through open plains, navigating uneven volcanic landscapes, and retreating into wooded shelter when necessary. The pelvis likely resembled an intermediate stage between the wide, flared configuration of Australopithecus and the narrower, more efficient structure of later Homo species. This shape supported habitual bipedalism while allowing for the birth of infants with slightly larger heads. Such pelvic adaptations reinforce the idea of prolonged developmental periods, which in turn required stronger social networks and greater parental investment. A species with slower maturing offspring needed cooperation, shared foraging responsibilities, and mechanisms for group cohesion. These requirements become even more pronounced when communities lived in landscapes filled with danger from predators and competition from other hominin species. Thermoregulation also played a critical role. The broad nasal aperture of Rudolfensis suggests adaptations for conditioning dry, hot air during inhalation, crucial for maintaining hydration and protecting delicate respiratory tissues. This feature aligns with the increasingly arid conditions that characterize the region. It also hints that Rudolfensis engaged in extended daily movement, as efficient nasal airflow contributes to sustained physical activity. Though not the long-distance traveler that Homo erectus would become, Rudolfensis was clearly suited for regular foraging trips that spanned wide areas. Subtle details of the skull provide further complexity. The shape of the temporal lines, ridges along the skull where chewing muscles attach, illustrates a species that invested heavily in mastication, but not to the extreme seen in Paranthropus. This intermediate level of specialization mirrors the species' ecological role, not a pure generalist, yet not entirely committed to any single dietary strategy. This anatomical compromise may reflect a world where rapid environmental fluctuations prevented long-term specialization from becoming advantageous. Flexibility, rather than optimization, was the key to survival. Dental development patterns, observed through enamel growth increments, suggest maturation rates slower than Australopiths, but faster than later Homo species. This tempo places Rudolfensis in an evolutionary middle ground, capable of investing more time and energy in juveniles than its ancestors, but not yet requiring the extended childhoods seen in Homo erectus or Homo sapiens. Such intermediate development likely shaped group structure and daily routines. Young individuals would have required protection during foraging and sheltering, reinforcing cooperative dynamics within small groups. The shape of the cranial base reveals additional evidence of early changes in brain organization. Subtle flexion patterns, though not as pronounced as in later species, indicate shifts in how the brain balanced between expanded cognitive regions and legacy structures inherited from earlier hominins. These changes affected posture, the arrangement of airway passages, and the location of muscle attachments associated with speech-related movements. While Rudolfensis did not possess language as understood today, the anatomical groundwork for more complex communication was emerging. The capability for varied vocalizations, nuanced facial expressions, and intentional gestures would have strengthened social bonds and improved cooperative behavior, critical in a landscape with competing hominin species and abundant predators. Fragmentary limb fossils attributed tentatively to early Homo provide further clues. The curvature of hand bones in comparable species suggests an ability to grip objects with precision. This capability, combined with enhanced coordination implied by enlarged brain regions, opens the possibility that Rudolfensis made occasional use of simple tools, even if not to the extent of habilis. In an environment where carcasses, roots, and hard-shelled resources offered vital nutrients, even small improvements in tool-assisted access would yield major survival benefits. The lower limbs bore the unmistakable signs of habitual bipedality. Hip joint morphology from early Homo specimens indicates a stable, efficient gait well suited for walking across long distances in search of water, edible plants, and animal remains. Although the species may not have possessed the elongated legs that later allowed Homo erectus to expand across continents, Rudolfensis was far from sedentary. Its world demanded movement to track seasonal resources, avoid competition, and take advantage of fleeting opportunities in a rapidly shifting environment. What emerges from these combined anatomical insights is the portrait of a species finely tuned to cope with environmental volatility. Every structural feature, from the shape of the palate to the curves of the limb bones, reflects the pressures of a world in constant flux. Robust chewing anatomy offered insurance during food shortages. Expanded cognition provided adaptability. Efficient bipedal locomotion enabled individuals to navigate patchy landscapes. Social tendencies supported the lengthy care required by developing offspring. The species carried a toolbox of biological strategies designed not for dominance, but for endurance in a challenging ecological theater. Yet this anatomy also carried limits. While Rudolfensis possessed versatility, it lacked the specialized advantages that allowed its contemporaries to succeed in specific niches. It also lacked the transformative combination of mobility, endurance, and advanced cognition that later enabled Homo erectus to spread far beyond Africa. These evolutionary trade-offs shaped its destiny. In a world that favored rapid movement and more sophisticated foraging techniques, Rudolfensis remained tied to a body built for an earlier era. As environmental pressures intensified and new competitors rose, these limitations gradually narrowed the ecological space available to the species. Even so, the anatomical legacy of Homo rudolfensis offers invaluable insight into the early stages of human evolution. It represents a pivotal experiment in balancing traditional hominin robustness with emerging cognitive capacity. Its existence reveals that the path toward humanity was neither linear nor uniform, but a mosaic of biological possibilities shaped by a world undergoing relentless transformation. In the next chapter, attention shifts from anatomy to behavior, exploring how Rudolfensis interacted with its environment, how it may have used tools, how it structured its social groups, and how its strategies compared with those of the species that eventually replaced it. Life in the early Pleistocene demanded far more than physical endurance. Survival depended on the ability to read shifting landscapes, navigate between rival species, and extract resources from an environment that offered opportunities only to those capable of recognizing them quickly. In this world, Homo rudolfensis developed behavior shaped by both anatomical possibilities and ecological stresses. Its actions, though impossible to observe directly, can be reconstructed through a combination of fossil evidence, comparative anatomy, archaeological context, and the behavioral patterns of closely related species. These clues reveal a portrait of a hominin navigating the threshold between instinct and innovation. The period in which Rudolfensis lived coincided with the earliest emergence of stone tool traditions. Although the species has not been linked to specific tool assemblages, the broader archaeological landscape of East Africa shows that simple stone flakes, cores, and anvils were widespread. These early tools, part of the Oldowan technological horizon, were primarily associated with Homo habilis. Yet the distribution of artifacts suggests that multiple species had access to them. The Turkana Basin was dotted with scattered clusters of stone flakes near water sources, often intermingled with animal bones bearing cut marks. Such sites indicate that hominins who understood the basic mechanics of striking stone to create sharp edges could access a wider range of food sources, especially meat and marrow. Given the cognitive capacity suggested by the cranial morphology of Rudolfensis, it is plausible that the species engaged with these tools, even if not at a consistent or systematic level. The broader brain case, increased frontal expansion, and enhanced visual motor coordination point toward an organism capable of recognizing cause and effect relationships. If Rudolfensis observed other hominins using stone flakes to open carcasses or to slice vegetation, imitation would not require complex teaching. Simple observation may have been enough. Even opportunistic tool use would have provided significant nutritional benefits, especially during dry periods when plant availability diminished. The ecology of the region further strengthens this possibility. Carnivore-dominated landscapes created frequent opportunities for scavenging. Predators such as saber-toothed cats left partially consumed carcasses that hominins could exploit if they acted quickly. Stone flakes were essential for cutting through thick hides and accessing high-calorie marrow locked inside bones. For a species with strong jaws but without extreme dental specialization, the combination of manual dexterity and opportunistic tool use could transform survival prospects. The ability to access protein-rich resources provided an evolutionary advantage in environments where competition for plant-based foods intensified during droughts. Behavioral patterns, however, extended beyond feeding strategies. Social structure played an equally vital role in the daily lives of Rudolfensis. A larger brain typically correlates with increased group complexity, longer developmental periods, and more sophisticated interactions. While the fossil record cannot confirm specific group sizes, environmental challenges strongly suggest that individuals lived in small, cooperative units. These groups likely ranged across the landscape together, protecting vulnerable young, sharing knowledge of seasonal food sources, and providing mutual defense against predators. Cooperative behavior would have increased resilience during periods of scarcity, particularly when access to water and food shifted unpredictably. Group cohesion was also shaped by the developmental biology of the species. Larger-brained hominins tend to have infants with slower growth rates, requiring prolonged parental investment. Juveniles dependent for longer periods would have relied on adults not only for protection, but also for learning basic behaviors necessary for survival. This extended learning window opened the door for transmission of knowledge, an early precursor to cultural behavior. Although Rudolfensis did not possess language as understood today, vocalizations, facial expressions, and gestures likely served as communication tools. Such signals would have conveyed danger, coordinated movement, and reinforced social bonds. The landscape itself influenced movement patterns and group behavior. The Turkana Basin consisted of alternating zones of open savanna, forest patches, and wetland corridors. During wetter periods, hominin groups may have stayed near lake shores, where vegetation and animal life were abundant. When the climate shifted toward aridity, these groups were forced to travel greater distances in search of resources. Seasonal migration patterns seen in modern ungulates likely influenced the behavior of early hominins, who may have followed herds to access grazing animals and their predators' leftovers. These seasonal shifts would have required detailed spatial memory, route planning, and an understanding of where water and shelter could be found during extreme conditions. Evidence from nearby fossil sites shows that early Homo species frequently revisited specific locations rich in predictable resources, such as riverbanks where stones suitable for tool-making accumulated. This behavior suggests a cognitive awareness of place, a mental map shaped by repeated experiences. Homo Rudolfensis, with its expanded neural architecture, likely participated in similar patterns. Understanding landscapes at this level reflects a shift in the relationship between hominins and their environment, no longer merely reacting to immediate conditions, but anticipating future needs. Interactions with other hominin species further shaped the behavior of Rudolfensis. The Turkana Basin hosted multiple human-like species, each with distinct ecological roles. Homo habilis, with more consistently demonstrated tool-making skills, would have been a direct competitor for carcasses and plant resources. Paranthropus boisei, though specialized, occupied overlapping territories and may have indirectly competed by altering vegetation in ways that influenced resource availability. The coexistence of multiple species created a landscape filled not only with predators and prey, but also with hominin rivals. These interactions may have influenced territoriality, movement choices, and even group dynamics. A species unable to secure vital resources could be forced into marginal habitats, increasing vulnerability. While evidence of direct encounters between species is absent, The ecological overlap suggests frequent visual and auditory contact. Seeing another group at a waterhole or observing tool use from a distance could have influenced behaviors through imitation or avoidance. Competition may also have encouraged the refinement of strategies that improved survival, selecting safer pathways, seeking more reliable food sources, or altering foraging patterns to avoid peak predator activity. These adaptive responses reflect growing cognitive sophistication and the capacity to adjust strategies based on experience. The broader ecological pressures also likely encouraged Rudolfensis to develop a flexible daily rhythm. Early mornings and late afternoons offered safer conditions for movement, as many predators were less active at these times. Midday heat in open savannas forced hominins to seek shade, rest, or engage in activities that required less exertion. Such patterns are consistent with the behavior of later Homo species and modern primates living in similar climates. The ability to adjust activity levels according to environmental cues is an essential behavioral adaptation for thermoregulation and energy conservation. Water played a central role in structuring movements. Lakeshores provided hydration, plant foods, and access to animal carcasses. But they also attracted predators. Groups likely approached these areas with caution, staying alert and positioning themselves strategically to detect danger. Observations of modern primates and human foragers offer parallels. Individuals scan the landscape while others drink or forage, creating a pattern of rotating vigilance. Such simple cooperative behaviors dramatically increase survival rates and require only modest cognitive abilities well within the capacity of Rudolfensis. As the species interacted with the environment, its behavior also shaped the environment in return. Repeated access to specific areas, trampling of vegetation, and selective harvesting of plants would have subtly altered ecosystems. Even without fire or advanced tools, hominins influenced seed distribution, soil compaction, and predator-scavenger dynamics. These small ecological footprints represent the earliest stages of humans becoming active participants in shaping their surroundings, rather than merely responding to natural forces. The presence of stone tools across the region raises another question. Did Rudolfensis develop its own technological traditions, or did it rely primarily on opportunistic access to tools made by other species? The answer remains unresolved, but the potential for innovation existed. The species' cognitive structure suggests that Rudolfensis possessed the necessary motor skills and visual spatial awareness to strike stones and create flakes. Even limited participation in tool-making would have broadened access to nutritional resources. Over generations, this intermittent practice could have contributed to a gradual cultural evolution, though not one that left dense archaeological signatures like the Acheulean tools later associated with Homo erectus. Another behavioral dimension emerges when considering the likely social interactions within groups. Hominin societies of this period were not dominated by hierarchical structures, but were shaped by cooperative survival. Food sharing, particularly of high-value items like marrow or fruit, would have reinforced trust and reciprocity. Group members likely recognized individuals through visual and auditory cues, forming bonds that persisted across seasons. Such recognition would have been crucial during migration or when reassembling after spreading out during foraging. These early social dynamics laid the groundwork for more complex cultural systems that would appear in later Homo species. Reproductive behavior and mate selection also played a role in group stability. Hominins with prolonged juvenile dependence required stable social environments to raise offspring. Adult cooperation in childcare increases survival rates in species with long developmental periods. This model is consistent with Rudolfensis, whose cognitive and dental development suggests slower maturation than earlier hominins. Cooperative breeding strategies, in which multiple adults assist in raising young, may have emerged during this period. Such strategies promote group cohesion and allow individuals to engage in foraging activities while juveniles remain protected. Environmental unpredictability would have amplified the importance of such social networks. Droughts, volcanic disturbances, or sudden shifts in animal migrations could fragment food availability. Groups that maintained strong social bonds were better equipped to adjust, whether by relocating, sharing scarce food, or collectively avoiding dangerous areas. These adaptive responses illustrate the beginnings of behavioral complexity that distinguished early Homo species from their more instinct-driven ancestors. As climate cycles grew increasingly extreme, Homo Rudolfensis existed in a world where behavioral flexibility became as important as anatomical robustness. Its capacity for observational learning, memory, cooperation, and opportunistic use of tools positioned it as one of the earliest hominins to balance instinct with strategy. Yet these same qualities, while beneficial, were not sufficient to compete with the emerging capabilities of Homo erectus, whose greater endurance, advanced tool-making, and wider territorial range allowed it to dominate landscapes once shared by multiple species. The behaviors of Rudolfensis reveal a species navigating a delicate balance: resourceful but not specialized, intelligent but not yet transformative, cooperative but not structured enough to withstand the ecological and competitive pressures of the early Pleistocene. Even so, its existence marks an essential stage in the evolution of human behavior. The seeds of social complexity, environmental strategy, and cognitive flexibility took root during this period, setting the stage for the dramatic evolutionary shifts that would follow. In the final chapter, the decline of Homo Rudolfensis and the rise of Homo erectus will be explored, revealing the forces that reshaped the hominin world and how the disappearance of one species created space for others that would ultimately shape the destiny of humanity. The end of Homo Rudolfensis unfolded gradually, shaped by forces far larger than any single species could control. Between 2.0 and 1.8 million years ago, East Africa entered one of the most intense climatic reorganizations in its geological history. Rain cycles became more erratic, savannas expanded unevenly, forests receded, and the distribution of lakes fluctuated with sudden intensity. These shifts reshaped entire ecosystems, redirecting river flows, altering migration patterns of herbivores, and transforming fertile regions into arid zones within a few generations. For a species dependent on flexible feeding strategies, but lacking the advanced mobility seen in later Homo forms, this relentless environmental restructuring posed an existential challenge. The decline of Rudolfensis cannot be linked to a single catastrophic event. Instead, it was a long, quiet contraction, an erosion of ecological space that unfolded as other species emerged with traits better suited to the evolving landscape. The rise of Homo erectus stands at the center of this shift. Appearing around 1.9 million years ago, Erectus introduced a radically new adaptive profile. Elongated legs suited for endurance walking, narrow hips optimized for thermoregulation, a more efficient stride, and a cranial capacity trending upward. This combination of physical and cognitive traits allowed Erectus to move across vast distances, follow herds across open plains, and exploit a wider array of habitats compared to its predecessors. As Erectus spread across East Africa, the competition for resources intensified. Both species occupied similar ecological niches, relying on a mix of scavenging, opportunistic hunting, and plant foraging. However, Erectus demonstrated a level of endurance unmatched by Rudolfensis. Its body shape, with a taller stature and improved heat dissipation, enabled extended foraging excursions into open terrain where daytime temperatures soared. This advantage allowed Erectus to access carcasses before they decomposed or were claimed by predators, travel between scattered water sources during droughts, and retreat from deteriorating environments more effectively. The emergence of Aculean tools, although appearing slightly later in the archaeological record, indirectly reflects a broader behavioral shift already underway. Earlier forms of Erectus likely practiced increasingly complex tool-making behaviors, even if the earliest stone artifacts associated with them remain Oldowan in style. Greater planning depth, consistent use of flakes, and efficient butchering strategies provided Erectus with a crucial edge in nutrient acquisition. These tools allowed individuals to penetrate the thick hides of large mammals, process resources more quickly, and exploit environments that demanded greater technological support. For Rudolfensis, whose anatomical robustness compensated for limited tool use. This technological leap created a widening gap. Environmental pressures magnified these disparities. As forests contracted, species that depended on shaded habitats or mixed woodland resources found their ranges shrinking. The broader face and chewing apparatus of Rudolfensis suggest an ability to process tough plants, but not with the extreme efficiency seen in Paranthropus. Likewise, its dietary flexibility was valuable, but not inexhaustible. When cycles of extreme aridity reduced plant diversity, or compressed populations into tight ecological zones near water sources, Rudolfensis faced direct competition not only from Erectus, but also from Habilis and Paranthropus. Every drought season intensified this overlap, concentrating multiple hominin species in diminishing refuges where survival depended increasingly on endurance, cooperation, and technological advantage. These environmental pressures also altered predator dynamics. Carnivores became more concentrated around waterholes and migration corridors as herbivore distributions fluctuated. Hominins traveling through fragmented landscapes faced increased risks. Groups capable of traveling farther and navigating predator-filled savannas with speed and coordination had greater survival odds. Erectus, with its longer stride and improved stamina, fit this model. Rudolfensis, built for brisk movement but not extended endurance, found itself increasingly at the margins of a landscape that no longer accommodated intermediate forms. The fossil record shows a marked decline in the presence of Rudolfensis specimens after approximately 1.83 million years. This disappearance is gradual rather than abrupt, suggesting that the species survived in small, isolated pockets for some time before vanishing entirely. Such isolated groups may have experienced genetic bottlenecks, reduced access to mates, and limited population sizes. In fragmented habitats, evolutionary pressures often accelerate extinction when species cannot maintain genetic diversity or adapt rapidly enough to new challenges. In the case of Rudolfensis, the combination of ecological displacement and demographic stress likely contributed to its fading presence. Despite its eventual disappearance, the species' contributions to the greater evolutionary picture remain significant. Its existence demonstrates that brain expansion in early Homo was not a singular, linear process. Multiple lineages experimented with increased cognitive capacity, each shaped by varying degrees of environmental flexibility and anatomical constraint. The relatively large brain of Rudolfensis, paired with robust chewing adaptations, shows that evolutionary pathways can diverge unexpectedly. This divergence challenges the traditional assumption that early brain growth required immediate facial reduction or reduced dental size. Instead, Rudolfensis reveals an evolutionary scenario where multiple functional demands coexisted, producing an organism capable of navigating diverse dietary landscapes. The evolutionary experiments represented by Rudolfensis underscore the complexity of human origins. Rather than a steady progression toward modern human traits, the early Pleistocene showcases a dynamic branching pattern. Some lineages pursued dietary specialization, others relied on technological innovation, and still others balanced anatomical versatility with emerging cognitive traits. Each lineage contributed differently to the mosaic of human evolution, even if not all persisted. In this context, Rudolfensis occupies a critical position as one of the earliest forms to exhibit notable brain expansion without losing ancestral robusticity. The decline of Rudolfensis also marks a turning point for the Homo lineage as a whole. With Erectus becoming dominant, the landscape began to favor mobility, endurance, and technological planning over anatomical specialization. Erectus pushed the boundaries of hominin adaptability, eventually expanding beyond Africa to populate Eurasia. This continental dispersal represented a level of ecological flexibility that earlier species, including Rudolfensis, could not match. The disappearance of Rudolfensis thus reflects the broader evolutionary transition from early, regionally confined hominins to a lineage capable of global expansion. The legacy of Rudolfensis is preserved not through descendants, but through the insights it offers into early human diversity. Its morphology, behavior, and ecological strategies highlight the importance of evolutionary experimentation. The species lived during a period when climate cycles forced rapid adaptation, when multiple hominin forms overlapped and competed, and when cognitive complexity was only beginning to reshape survival strategies. These pressures created a natural testing ground that determined which traits would continue forward in the Homo lineage. The fossil evidence from Turkana remains a reminder of how much evolutionary history is still missing. Fragmentary skulls, scattered teeth, and partial jaws offer glimpses into a species that likely displayed greater diversity than any single specimen can represent. New discoveries may reveal additional anatomical traits, expand the timeline of the species, or refine its ecological role. Each fossil adds a piece to a puzzle that continues to evolve, emphasizing that human origins remain a field defined by questions rather than definitive narratives. Even in absence, Rudolfensis continues to influence modern interpretations of human evolution. Its existence demands a reevaluation of how early Homo species interacted, how brain expansion emerged, and how multiple lineages attempted to solve the same challenges in different ways. This species was part of a complex evolutionary web, rather than an isolated ancestor. Its disappearance, therefore, does not signal failure, but rather illustrates the competitive and dynamic nature of early human evolution. The final lesson of Rudolfensis lies in the realization that extinction is not synonymous with insignificance. Species that disappear without leaving descendants still contribute to the evolutionary landscape by shaping the selective pressures and ecological contexts that influence the survival of others. The presence of Rudolfensis in early Pleistocene ecosystems altered competition patterns, resource distribution, and predator-prey dynamics, indirectly influencing the evolutionary trajectory of species like Erectus. Today, the story of Homo Rudolfensis stands as a reminder that human evolution was shaped by diversity, competition, climate, and chance. It represents a lineage that came close to forging its own evolutionary path, but ultimately stepped aside as new adaptive strategies emerged. Its fossils embody possibilities, paths not taken but crucial to understanding the complexity of what humanity has become. Don't forget to subscribe. It really supports the channel and helps us bring you more great stories.